Hey everybody, today we're going to do a number of examples playing around with BodePlots to get you familiar with some of the mechanics of doing that. I'm Michelle Maharvez.
And I'm Vivek Subramanian. Let's get started. Now you'll recall that in the last section where we introduced the idea of BodePlots, one of the last things we looked at was this table. And this table lists some of the common forms that we use to build a BodePlot. In other words, there's various poles and zeros. And if you need to review what the poles and zeros are, you should go back and review the previous module. But we're going to use this table here to analyze transfer functions. So here's what we're going to do. We're going to take an arbitrary transfer function, and then we're going to figure out, using the terms in this table, how to create a BodePlot. So we're going to sort of take that transfer function, find representative terms such as these. So zeros at origin, poles at origin, simple zeros, simple poles, and so on, and try to use those as components to build a full BodePlot. So let's start by doing a simple example. And the example, of course, will start with a transfer function, some arbitrary one. So I'll pick this one. So this is some arbitrary transfer function, and you'll see it has some terms in the numerator and some terms in the denominator. Now, if you go back and you look at this previous one, what you find is that all of these terms, let's take for example the simple zero. They're organized in very specific ways. Like the simple zero is organized in a 1 plus j omega over something, which we're calling omega c here. Similarly, the simple pole, which shows up in the denominator, is organized as 1 plus j omega over something. So what we need to do is then we need to take this transfer function and we need to organize it in that form. So turns out to be the first step, and in many cases the most difficult step in doing BodePlot analysis. It's often hard to sort of look at these and figure out how to break it up into its component forms. So we're going to do it, but really the only way that you can get the hang of this is through practice.
Okay, so but looking at it, you could see that there's three features, even though we don't have them in the right form. There is something real plus a j omega, and it's got an exponent of 2. So that's probably going to be a 0 with an n of 2.
Correct.
You're going to have another one down here in the denominator of the same form, right? It's something real plus j omega something.
Correct.
N of 1, so that's probably going to be a pole. And then you've got a 1 over j omega something, so there's probably going to end up being another pole down here.
Right, exactly right. And in fact, if you back up, you can already see. So we had a 1 plus j omega in the numerator, so that's probably some form of a simple zero. We had 1 plus j omega in the denominator. That's probably something in a simple pole type. And then we had a j omega in the denominator, and that's probably going to be a pole at the origin.
Okay. So the game is going to be kind of factoring numbers to get them into this
Exactly.
form. Okay,
So let's go back and go ahead and do that, okay? So I'm going to do it for you, and I'm just going to show you the outcome, and then you'll see how it works. The reality is, in many cases, this is the real meat of the problem, is figuring out how to factor this out. Okay, so here's how I've sort of reorganized it into standard form. I want it to be in a 1 plus j omega form. So look at the numerator. The numerator is in a 20 plus j omega something form. If I want it to be in a 1 plus j omega form, what I have to do is bring terms outside. Now this is square, so I bring the term outside by bringing 400 out.
Got it. So
that it remains in a 1 plus j omega form. Okay?
I see. And 4 over 20 is
1
over
so
5.
That's where you get that. Okay, perfect. So that becomes over 5. And then similarly in the denominator, it's in a 100 form, so I bring the 100 outside and it becomes in a 1 plus form. Okay? And so now it's something closer to what I want. I have a 1 plus j omega over something in the numerator, I have a 1 plus j omega over something in the denominator, and I have a j omega over here. Now, here I can simplify the terms outside the parentheses because it's 400 over j omega 4000. Right?
So the 400 over 4,000 would just turn into 0.1.
So it turns into 0.1. And so just, actually, Michelle, let me ask you if you can explain this. So it should be, according to my math, it should be 0.1 over j omega, yet I've written it here as minus j.1 over omega. What's that?
We've tried this, we've played this trick before where a minus j in the numerator can become a j in the denominator. Remember, 1 over j omega c is equal to minus j over omega c.
Right. Okay. That's all this is. So you can write it in either form. Sometimes you might feel more comfortable just leaving the j in the denominator, and that's completely fine.
I do. In fact, I would have thought that I would have put the j in the denominator and called that a pole.
Yeah. So that's fine. Just remember that you can recognize it that way.
And the 0.1, by the way, that's just that k factor. That's just a multiplier. If you go back to the table, we'll show it to you in a minute.
Right.
But that's just a multiplier.
So that's how we set this up. All right. So let's go ahead and get started. So let's look at this and let's break these apart. So looking at the standard form, Michelle, what do we see? You see, first let's take this first term here, the one that I'm pointing out right here in the numerator. What is that?
Okay, reading just below, I see that it is a simple 0. It's got second order, which means that the n is 2 up on the top right. The exponent is 2. And it's j omega over omega c, so omega c must be 5.
Exactly. Okay. And similarly, if we look in the denominator, now you'll see that there's actually 2 poles that exist here. One pole is the pole associated with the simple pole, so 1 plus j omega over 50. So now this is not a second order term because it's not raised to any power. Okay, so but it's going to have a center frequency, a corner frequency sitting at 50. And then there is another pole at the origin associated with this term right over here.
The 1 over j omega.
Right, exactly. Okay, so we've identified all the terms. Now what we're going to try to do is we're going to try to build them up. And what I'm going to do while I do this is I'm going to flip back and forth between the table and the Bode plot that I'm about to show you, just so that we can highlight each one by one. Okay? And if you're working on Bode plots, frankly, it's often helpful to just have that table available to you. It makes life easier. Okay? Now, here's what we're going to do. First, we'll just do it sort of mathematically, and then we'll plot it all up so you can see how this works. We can figure out the magnitude and phase from this form by converting it to dB and taking advantage of the Bode plot formalism that we'd set up earlier. In other words, so we'll take each of these and we'll sort of work them out. If we're converting it to dB, the advantage is things that are multiplied, we add together in log
that was
space.
the trick, right? That's
right?
the beautiful trick of the dB.
Right. The dB scale allows us to take all these individual factors and now write them in a log scale as adding terms. So let's take that first one. We'll get 20 log 0.1, okay? Plus, it's plus because we're multiplying, 40 log 1 plus j omega over 5. Michelle, why do you think I'm using 40 here?
Well, because the exponent is 2, so we bring the 2 to the front, and it's 20 times 2 log.
Exactly. It's a second order term. Okay? And that handles the terms in the numerator. Then in the denominator, we have minus 20 log omega. The minus is because it's in the denominator, of course. And then we have minus 20 log 1 plus j omega over 50. Okay? So that's basically what we have over here. And you can simplify this further if you need to. So, for example, you can calculate out what the log of 0.1 is, right, and just simplify. But that's fine. We'll deal with that later. Similarly, we can set up the phase. And when we set up the phase, we see that there are 3 things that we have to deal with. So there's a 0, okay, and it's a second order 0. And there's 2 poles. One pole is at the origin, and the other pole is a simple pole.
Okay, so if I remember correctly, a 0 at the origin has a flat 90-degree constant sort of phase shift, but a pole at the origin has a minus 90-degree.
That's right.
So that's the minus 90 degree. That's
the
pole at the origin.
Yeah, the pole at the origin has a flat minus 90 degree, and then we have
2 times and then
two
the
times the arctan associated with the 0 because it's a second order term, and an arctan subtraction associated with the pole, the simple pole.
Okay.
Okay, so that's the idea. Now these are the actual mathematical forms of the equations, but let's go ahead and do what we came here to do, which is generate the Bode plots. Okay, so this probably scares the bejesus out of you when you see it.
That's what I thought when I saw it.
Okay, so here's what we're going to do. We're going to make
We have to explain it.
Yeah, we have to explain it. Okay, let me set this up for you. I'm going to tell you that by the time you're done, firstly, there's 2 plots, the plot on the top and the plot on the bottom. The plot on the top is the magnitude plot, so it's the m function. The plot on the bottom is the phase plot, so it's the phi.
Right.
Okay? Let's focus on the magnitude plot to start. And you'll see there's all these colored lines, and we have a blue line, a light blue line, a green line, sort of a dark blue line, and this red line. The red line turns out to be what the final Bode plot looks like. Okay?
I see. Okay.
So hold that thought, and let's just work through these one by one.
The red is the answer.
The red is the answer. Okay? Let's work through these one by one. So let's take the standard form. We can just do it off the standard form. So the standard form, what I'm going to do is I'm going to generate individual plots for each of the terms in the standard form. All right, Michelle, just because life is easier with, personally, I'm much more comfortable working with the simple poles and simple zeros.
Sure.
Let's start with the simple zero.
Okay, so the simple zero is going to have a corner frequency at 5, omega of 5 radians per second.
Correct. Okay, hold that thought.
Okay, so let's go to...
All right, let's look at the table. We're going to do a simple zero. Okay, and the simple zero has a form of 1 plus j omega over omega c raised to the n, okay, where n is the order. And what it's going to do is, you told me the corner frequency on that previous one was 5. So what you're going to do is you're going to draw a flat line, and then at the corner frequency you're going to go up. And the slope going up is 20 times n.
So ours will be 40.
Exactly, because we have a second order term. So the light blue line represents what, if we had just that simple zero in our transfer function, this is what the contribution would look like. So flat till that corner frequency, which is 5, and then it would go up at 40 dB per decade.
Okay.
Okay? Now, let's do another relatively easy one. Let's do that simple pole.
Okay.
So let's again start by defining the corner frequency.
50.
50. Good. So let's do the simple pole. So if we look at the simple pole, same deal. We stay flat till we hit the corner frequency. Then it drops at 20 dB per decade times n, where n is the power.
And n is 1, so it's minus 20.
Exactly. n in this one is 1 because it's not raised to anything. It's a first order term. So it's going to go flat
Till 50.
till 50 and then drop at 20 dB per decade. So if the simple pole were the only thing we had in our transfer function, it would look like this sort of dark blue line.
Okay.
Okay? All right. Now, let's do the last one.
Pole at the origin!
Pole at the origin. Okay, so let's go ahead and look at how we deal with a pole at the origin. If we look at a pole at the origin, it's actually pretty easy to deal with. It's a line. So the pole is j omega to the minus n, so it's going to have a j omega in the denominator. And what it should do is drop at 20 times n dB per decade and go through 0 dB at an omega of 1.
So basically, you know that the exponent always tells you something about the slope.
Exactly. The exponent tells you how many 20s you have in the slope.
Okay.
Okay? And the pole at the origin will always go through 1.
All right.
So, first tell me, what's the order of the
It's 1.
pole? Okay, it's 1, so it's going to drop at 20 dB per decade, and it's going to go through 1.
And that's the green line.
That's the green line. Okay, now so we've got the individual contributions lined up. Then all we do is we're going to do graphically what we did mathematically over here.
Mm-hmm.
In other words, we're just going to add all of these up.
Okay.
Okay? So, how do we deal with that? Well, we take advantage of the fact that we have to add these terms together, but there's one more thing we have to deal with. And the one more thing we have to deal with is I've identified the pole, but what about the flat value?
Aha!
Aha. Okay.
Go to the chart.
Well, we'll go to the chart and let's look at constants. So if we just have a constant, what do? It's a flat line. Okay? And the flat line sets what the value is. Okay? So, go back, and we had 0.1.
So that's
Okay.
10 to the minus 1.
It's 10 to the minus 1. Okay? And it's 20
Times 10 to the
log of 10 to the minus 1, so it's minus 20.
Minus 20.
So the last piece of information we needed before we put everything together is the dashed light blue line, which is the contribution of the constant. So now we're going to add all of these together.
So the way I do it, by the way, is I do all of the poles and zeros, and then when I'm done, I can shift that whole curve up or down by the minus 20 dB in this case.
Exactly, which is why we started by sort of figuring out all the poles and zeros, and then right at the end we did the shifting by defining this term. So we're going to add all of these together, okay? So we've got a minus 20 dB flat line, and then we're going to calculate the contributions from everything else. So, Michelle, up to a frequency of 1 radian per second, do you agree that the simple poles and zeros are both not contributing anything, they're both sitting at 0?
There's 0. The green line has some value.
Right, so this green line has some value right over here. So what we're going to do is we're going to add the green line to the dashed blue line, and what we're going to get is we are going to shift this up. Okay, so we're going to get this part of the red line.
Mm-hmm.
And it's going to follow that. It's just shifted 20 dB down, okay, until we hit this first simple 0.
The first corner, yeah.
The first corner, and then it's going to climb up. And it's going to follow that until we hit this first simple pole, when it's going to flatten back out again.
Notice it climbs up between 5 and 50 because the slope down is 20, but the slope up is 40.
Is 40, exactly.
So you get a net 20 up.
Right. So anytime, this is a good point. Anytime you see a transition because you hit a corner, you can figure out the net change in slope based on the order of the terms that you're adding or removing. Okay? And so that's that. That's the easy one. Now, we can do the same thing for the phase. Phase, so what's the rule? The rules for phase are pretty simple. Let's go to the table again. The rules for phase is, if you have a simple 0, you go from, if your corner frequency is omega c, you'll start at 0, 1 order of magnitude below, 1 decade below omega c, and go to 90, 1 decade above omega c if your order was 1. If your order is 2, you'll be going from 0 to 180, and so on and so forth.
And by the way, the 0.1 and 10 don't really mean anything. It's just the person that came up with this set sort of a reasonable place to do the corners.
Right.
The real shift is very gradual.
Right. The real shift is asymptotic, and you'll see that later.
Yeah,
but this sort of represents that. Okay. And so what we've got is we can take each of these and draw the individual components. We'll follow the same methodology. Okay. So we have. Again, we're going to draw it at our, let's first take our simple 0,
okay,
which means it's raised to a second power.
So it's going to go 0 to 180.
It's going to 0 to 180, and it's going to be in the middle at the corner. So it's going to go 0 to 180. It's at, the corner is at 5, so that's going to be at 90. 0 is going to be at 0.5, and 180 is going to be at 50.
Okay.
Okay? Now let's do, Michelle, why don't you take on the simple pole?
You want to give me something to do so I stop interrupting? Is that what's going on? So you take the pole. Yeah, it's centered at 50.
Okay, good.
It's going to be going down between 0 to minus 90.
Yep.
Okay.
And it's the center is at 45. Or minus 45.
The center is at minus 45.
Degrees.
Oh, minus 45 degrees. Yes, absolutely. I thought you were telling me minus 40. Yeah, so it's 50 is the center, and then it goes from 5 to 500, and the center is at minus 45. Exactly. Right. That's right.
Okay. And then the other terms turn out to be fairly easy to deal with. The constant contributes nothing. Okay. And then we are left with the pole at the origin, the 0 at the origin, sorry, the pole at the origin, and the pole at the origin will sit at minus 90 degrees.
That's right.
And you can see that from the table. If you look at a pole at the origin, it's a flat line at minus 90. If you look at a constant, it sits at 0. Okay? And so we're basically done. Again, we put these together, and we get the red line. So you've done your first Bode plot. Make sense?
It does to me.
All right. Maybe we can move on, and Michelle, you can do another example.
Let's try another one. Okay. So let's take a transfer function that looks like this. So this is going to be, again, you're going to end up having a combination of zeros and poles. And just looking at this one, you notice that you've got something here raised to an exponent of 2. It's probably going to give us a 0 with an n of 2. But then you got this sort of weirder one down here. Now, of course, those of you that look carefully at the table notice that we had quadratic zeros and poles in that table as well, and that's where this is going to come into play. Okay? Now, once we factor, we get 3, and then you get this 1 plus j omega over 3 to the n equals 2, 0, so that's going to be a simple 0 at omega of 3. And then you're going to get this quadratic pole here. Now that's going to take a second to sink in. You'll notice that omega c for that quadratic pole is 10, and the order, because it's a quadratic pole, is 2. But let's take a look at that one. So I'm going to go back and take a look at the table. Okay? So notice this is the form. The n is 2 there. And the center frequency, which we saw was 10, I'll come back to it in a second, it's right there. Now we're going to expect this one to drop at minus 40 times n. So it's going to be steeper, and it's going to go between 0 and minus 180 times n. So these shifts, they shift more in degrees. If it's a 0, it goes up. If it's a pole, it goes down. And it's also going to have a steeper slope down in the case of the pole for a quadratic one. Okay?
I have to say the hardest thing with quadratics is factoring them out. That's the real pain with quadratics.
These are horrible. I mean, that's the truth. So you can spend a little time seeing, just like we did in the last example, how we factor this out to get the 1 plus. And this is actually a pretty easy one, to be honest with you, right? But they can get, particularly combinations of quadratics can get kind of hairy. But moving on, once we have it in this form, it's pretty straightforward. So again, we notice there's just three things. There's the k, there's the 0 here with an n of 2. It's a simple 0 at omega 3. And then there's the quadratic pole. Okay?
So let me ask you a question, Michelle. Sometimes I struggle with deciding without looking at the equation or factoring it out. How do I decide whether to leave it in whether it's a quadratic or perhaps it is two simple poles?
Well, the way to notice, see this term had a real part, an omega squared part, and an omega part.
Yep.
And so if you can factor this, as you learned, essentially in algebra, if you can factor it into this form, that's going to be quadratic. In other words, this is a quadratic, right? You get the 3 omega squared plus j90 omega plus 300. You wouldn't see that if you look carefully. See the simple one? The simple one doesn't. You can't. You couldn't do that. You can't put it into this form. Does that make sense?
Not really, but
okay.
I guess the short answer is, the point we're making is this is harder and you have to, sort of recognizing whether you can factor it or not, it often just takes practice.
Oh, the answer you wanted was, I can't tell very well, I just practice a lot until I kind of pattern recognize it. Okay, that's fair. But going back to this, so you've got the three parts, you've got the 20 log 3, you've got the 2 there, so that's 40 log.
From the 0. Second
and
order 0.
That's right. And then minus, because it's a pole, 20
right.
log, and then
and that's the complex. That's the
magnitude of the
magnitude of the pole.
And then working out through this, we kind of 20 log 3 is 9.5 dB, and again these are the two components for the 0 and the pole. And then if you go back to the table, you'll see that the phase shift is actually pretty straightforward. Again, this is for the 0 at 3, so it's got an exponent of 2, so 2 arctan of omega over 3, and this is the
that's the second order.
The second order. Okay. Now let's go through it. Probably a little bit faster than we did the first one, but just to kind of give you a little more experience. So again, what we've done is broken it all up. The final answer is in red.
Okay.
We expect what? What do we expect out of the magnitude?
Well, that's going to be a flat line shifted offset from 0. It's 20 log 3. I don't know how to calculate that, but you've done it for me. Haha, 9.5 dB.
Yeah, there you go. That's the green line.
All right, now let me do the easy one. I'm going to take on the 0, if you don't mind.
Sure.
So it's a second order term, so it's going to go up at 40 dB per decade, and it's going to have its corner at 3 because that's what it is over there.
That's right. There you go. So you got a corner at 3, 40 dB, done.
All right.
And then the last one, which we looked at, is the pole. And remember, the pole is at 10. The corner frequency is at 10, and it's just going to drop at 40 times n. The n of this is 1, so it's going to be minus 40 dB per decade straight down. So it's just steeper. That's all. Putting them all together, all of the poles and zeros, or the two of them are 0, so they do nothing, but you're shifted up by 9.5 dB, right? It's 9.5 dB plus whatever this is, which happens to be 0. Come along to the first corner, start heading up at 40 dB a decade. You see the red line starts going up. And then at 10, you've got a slope of 40 plus and a slope of minus 40, so the two of them add up to 0. They cancel out, and the line continues flat, and that's the whole plot.
Makes sense. Okay, but now it's worthwhile, before we talk about phase, I noticed something that's sort of interesting. It looks like you can, just by looking at the change in direction, sort of the slope, you can figure out whether you hit a pole or a 0. Because anytime you hit a 0, it's going to slope more upwards relative to where it was sloping earlier. Anytime you hit a pole, it's going to slope more downwards relative to where it was sloping earlier.
Yeah, that's exactly right. In fact, that's a really good way to think about it. You're coming along, and as you hit your first corner, if you start sloping up, that means you've hit a 0. If it levels off, that means that 0 was still there, but now you've got an additional pole that kicked in.
Because it pulled down the slope relative to where it was earlier.
Exactly.
Got
so
it.
you know there's a 0 with a corner frequency of 3, and that better be a pole with a corner frequency of 10.
Makes sense.
You can always back it out by looking at the Bode plot. The phase is pretty straightforward, again, by either looking at the chart in the slide previous, or looking at the expression. You're going to come up and your double zero is essentially going to jump between 0 and 180.
Yeah, because it's
right?
second order.
And
Yep.
the center is, of course, going to be at the corner frequency 3. That's going to be in the middle.
So then I'll go from 0.3 to 30, right?
Mm-hmm, to
Okay.
0.3 to 30. And then the quadratic, which is at 10, will turn at 1.
Right, so it'll go from 1 to 100, and it'll go from 0 to 180 because it's a quadratic.
Perfect. And so now you've got this blue line and then this dark blue line. You subtract them, you see as a minus, and so basically, or I mean, you're adding them. And then this thing is going to go 0, come up a little bit, but then this phase shift starts to kick in, so it flattens out and it comes back.
So this is kind of interesting. I always find it interesting to sort of think about what this means in terms of, I mean, we've been doing all this math, but what does it mean? Here you have a circuit, okay? There's some arbitrary circuit that has this transfer function.
Mm-hmm.
And depending on the frequency, you see that the gain changes. If this represented the gain of the circuit,
Mm-hmm.
the gain changes in terms of magnitude, but also you see that there's phase shifts.
Mm-hmm.
And you see that for low frequencies, there's no phase shift. In other words, what's going into the transfer function is coming out or is the same as what's coming out in terms of phase is what's on the output of the transfer function. But then there are regions where there's a 45-degree phase shift.
Which shifted off. That is
It's
interesting.
shifted up, right?
So let's. I think this is a good place to stop and emphasize that. I mean, this math is really here to show you what kind of interesting frequency responses you can get. Look at this one, and just let's take a step back from the math. I think Vivek's completely right. What is this doing for you? Just thinking of the magnitude, what is this circuit doing for us?
Well, if I look at the magnitude, so it's 9.5 dB. So that's a positive number, right? So that means that if it's and since I'm calculated from dB, if this is a voltage scale because it's we're doing it at 20 log of H, so that would suggest that it's effectively acting like an amplifier of some sort.
That's right. And for all the frequencies up to 3, it's amplifying, right? It's you're getting a larger. Let's say this was voltage to voltage, so you're getting a larger signal than you put in. And then when you're hit this corner, you start climbing so that after 10, you're amplifying a whole heck of a lot more. Because remember, this is a log scale.
Right.
That's a huge amount.
So this is kind of interesting. So here I have a circuit that has a certain gain at low frequencies, and then when I get to really high frequencies, the gain goes up even larger.
Yeah, exactly.
That's kind of neat. And it is also kind of neat that this phase shift occurs. So I'm going to mention something now just to sort of get you thinking about it. Imagine a circuit. Think about an op-amp circuit that uses negative feedback. Okay? You thinking of that, Michelle?
I'm thinking about it.
All right. So you got this circuit that has negative feedback. And let's say somehow because of my transfer function, for whatever reason, there's regions where the phase shift is 180 degrees.
Oh, okay, wait a minute. So you're saying the output is 180 degrees shifted from the input, and that's what I'm
Yes.
feeding back?
Yes.
So those things are going to overlap in a really weird way, right? Because whenever you're at a high point at the input, the output's giving you kind of the low node, right?
Right.
So would you just cancel everything out?
You'd actually, if you've got negative feedback and you're doing this, think about it. So when we talked about feedback, we said you'll have an instability associated with it effectively.
So it'll go the other way.
Right.
So it'll just keep building on itself.
Exactly. It's almost like positive feedback.
So you're saying, I see. So let's go think it again. If you had no phase shift and your input comes in and the same sinusoid comes out and it's negative feedback, I'm subtracting kind of one for one in a sense to the input, so I get the negative feedback. I get what you expect.
Right.
But now if it's 180 degrees phase shift, I'm sort of...
You're inverting and inverting again.
Exactly. So I'm adding it.
Right.
And this
It's
thing's just
positive,
going to ring up and get worse and worse, and you get positive
It's
feedback.
like a positive feedback case. So
That's a really cool example.
yeah. So you'll see these when we talk about some real circuit examples later, which we'll do. You'll see these. Let's now pick up on something Michelle said. Michelle said that you can look at the Bode plots and you can sort of back out what the transfer function looks like. Let's go ahead and do an example of that. Okay. So here's an example of some arbitrary Bode plot that I've given you. And let's first qualitatively look at this Bode plot and try to figure out what we're doing. So in our previous discussion, we said that anytime you hit a kink in the curve, based on whether the slope is increasing or decreasing, you can figure out whether you have a pole or a zero.
Oh, I get
Right?
it. Okay.
So here, what have we got here? Well, we're starting out at minus 40 dB per decade. And then we've got a kink, and it drops to minus 20 dB per decade, which means it's pointing less down than it was early. In other words, it's relatively speaking pointing up. So what do you think that would be, Michel, at this point?
So I guess when you hit that omega of 1, something must have kicked in that has a slope of positive 20 dB a decade,
Right.
so that effectively it goes from minus 40 to minus 20. You've raised it by
Yeah,
20.
and what is that?
That's a 0.
Yeah, it's a 0.
So there must be
exactly.
a 0 at 1.
Right, and then here...
And it's a first order 0 because it's only by 20.
Right, and now look over here. At 10, we've got another kick upwards, so there's probably another 0 there.
Again, of order of 1.
Right,
it went
because
from
it's
20
to 0, and then another one here, and then another one here. Okay, so qualitatively you see how this works.
Wait, but hold on.
Yeah.
What generated our first minus 40 dB per decade drop down?
That's a good
So
question.
it must be that there's 4 zeros and then it's going down, so that's it's a pole, right?
It is going down, so that will be a pole, and that's what order pole?
Second order.
Yep, second order.
Oh, and then
it's shifted, right?
and it intersects at 3 here.
At 3, yeah.
Huh.
Okay, so you know what the intersection point is, so you can figure out what the equation is. Let's go ahead and do it.
Okay, I see, I get it. Okay, let's
All
try
right,
it.
let's go ahead and do it. All right, so we can take these essentially step by step. So we'll do exactly what you did. You said you took that first line and you figured out that it intercepted at 3, right? And because it was 40 dB per decade, you know it's a second order pole, which means it's going to take a form of 1 over omega slash 3.
Ah, okay. Okay.
All right, and we can write that as 9 omega square. And you could test it, by the way, 9 slash omega divided by omega square. You can test it, by the way. You can sort of take this equation, convert it back into dB, and test it at some arbitrary frequency. For example, I might want to test it at this point right over here. I plug in an omega of 1, and I calculate, and sure enough, what I get is 19.1 dB. Okay, so that's not so hard. That's just to prove that we can do it. But this is the first one. Now we can add the next one in. Now, there's an important point to note, Michel. This line, I didn't start with a flat line that then went down. It was going down the whole time.
Right.
So can you tell me anything about that pole?
About the pole that was going down the whole time?
Yeah, remember, this pole didn't have a flat point and then it started going down. It was going down the whole time. What type of pole drops without having that kink?
Well, the poles at the origin, but those go through 1. So
Right.
then I guess that's why the 3 shows up there. It's basically it's like a pole at the origin, but it's centered at 3.
It's shifted, right. And further, I mean, shifting it up and down, we can also do, remember, we can also have a constant to shift the magnitudes, right? Okay, so that's the basic first formalism. Then let's go ahead and figure out the first kink. Now, the first kink is at 1. Okay, and you've already told me that this is probably a 0 because it's shifting upwards, relatively speaking, in terms of the slope. So we know the center frequency is at 1, and we know for what order is it?
What?
It's an order of 1 because it's going relatively 20 dB per decade, and it's going to be a 0. So it's going to take a form of 1 plus j omega, and the center frequency is 1. Then we can do the next one. The next one is at 10. Again, what's the order?
1.
1 because
Corners
it's 20
at 10.
dB shift. Corners at 10, so it's going to be 1 plus j omega over 10. And then we got another one at 50 and another one at 200.
And they're all zeros.
And they're all zeros because we only had the one pole to begin with, and then we had all of the others. Okay?
Okay, so let's see. Let me go through it again. You get a single 0 at the origin with an order of 2.
Correct.
A k of 9.
Correct.
Which, of course, 20 log 9 will give us
Right.
the 19.1 dB. That shifts that pole.
That pole.
And then you have 4 zeros that progressively shift the response to more and more positive slope.
Correct. Okay? Now, I've got all these individual contributions that I've now written as these factors. I multiply them all out, and I get the overall transfer function.
Oh, there you go.
Okay? And this is the overall transfer function. Now look at this, and you'll recognize it. So I've got an omega square in the denominator. It's not a 1 plus j omega, it's an omega square. So that would indicate a simple pole, okay, second order term. We have the constant, which is why this thing shifted out. Okay? It's just, the constant shifts it up and down, but the consequence of a constant shifting it up and down when you have a pole at the origin is that the number will shift where it intersects.
Exactly.
Okay? Then we have the 4 zeros.
Cool.
And that's it. Okay, so we've done our first example. You could also do it from the phase plot. Okay, and you can figure these out. The combination of a phase plot and a magnitude plot like this allow you to figure out everything. I often find it is just as easy to go from the factor form to the Bode plot versus from the Bode plot to the factor form. So they're both pretty easy to deal with. And I think this is a good stopping point now. We'll take a break from this. See you next time.
See ya.